Chapter 10, Part 2. In the previous part, we have learned how Grignard reagents are made by the reaction of alkyl halide plus magnesium in an ether-type solvent, and that usually gives you an alkyl magnesium halide. We have seen also how the similar reactivity when we compare the Grignard to the alkyl lithium. So we've seen how those reagents actually attack a carbonyl of an aldehyde or a ketone to give you an alcohol. So depending on what carbonyl structure it is, it will determine the classification of the alcohol. So for example, if I react a Grignard or an alkyl lithium with formaldehyde, that gives you a primary alcohol. If I react with an aldehyde, any aldehyde other than formaldehyde, like acetaldehyde or propanaldehyde or propanal or any other straight chain aldehyde, that will give you basically a secondary alcohol. If I have a ketone to react with those reagents, I will get a tertiary alcohol. So make sure that you look at those reactions that we have covered already in the previous part. Now, what we're going to see here is another option how we can make alcohol using a carbonyl structure, that is an acid chloride or an ester. Now, the most important thing to keep in mind here, that you're going to have two equivalents. I'm going to say two equivalents, not 2 moles, two equivalents. So regardless how much carbonyl you have, 2 times of that you need to have of the Grignard or the alkyl lithium. Why that is? Because the first one is going to attack the carbonyl, and we're going to see actually a full mechanism here. The first one is going to attack the carbonyl, is going to kick off the leaving group. So that's going to give you like a ketone structure. And then the second equivalent will attack the ketone intermediate to give you finally the tertiary alcohol. You're always going to get a tertiary alcohol. So keep in mind, whether I say 2 or I don't say anything, you need to assume that there is excess of the Grignard to attack the acid chloride or the ester. You always get an alcohol structure when you use Grignard or alkyl lithium, whether it's an aldehyde or a carbonyl of a ketone or an acid chloride or an ester, you always get an alcohol. So the Grignard reacting with an acid chloride, 2 equivalents of that will give us access to the alkoxide, followed by protonation will give me a tertiary alcohol. Same thing when I have the ester. So let's look at the full mechanism. The first equivalent of the Grignard reacting the acid chloride, obviously the R is the negatively charged part of the Grignard. We talked about that. Magnesium is 2+ formal charge. That gives a -1 for the X for the halide and a -1 on the carbon attached to the magnesium. So that's where the point of attack gonna start. The minus or the negatively charged carbon is gonna attack the carbonyl carbon, kicking up the pi bond. That gives me the tetrahedral intermediate. The O- is gonna restore the carbonyl, kick off the leaving group. What do you end up having? You're going to end up having a ketone. That's an intermediate. We never aim for the ketone structure in these reactions. You're always going to basically assume that there is going to be enough Grignard to go on to the next step. What's the next step? The ketone will react with another equivalent of Grignard, because you already have the first one attacking and already inserted the R group. The second equivalent, R magnesium halide, will attack the ketone. That will give you the alkoxide. Now you have 2 R group of the same, obviously, because you use 2 equivalents of the Grignard, and the R prime, which is already on the acid chloride. Now this alkoxide upon protonation, so that's why you need to have a second step, H3O+, to give you the tertiary alcohol. It's very important to keep in mind that you're always going to have 2 equivalents of the Grignard or the alkyl lithium when you have an acid chloride or an ester. Now, the aldehyde or ketones, you don't need more than 1 equivalent, because that will get you to the alcohol right away with that 1 equivalent. Now, what happens if you have a second equivalent? Well, it will be just a waste, obviously. Here's the ester. So if you have an alkyl magnesium halide, will attack the ester the same way how it attacked the acid chloride. So the negatively charged carbon attached to the metal will attack the carbonyl carbon, breaking up the pi bond. That gives you the tetrahedral intermediate. Restoring the carbonyl bond will kick off the alkoxide, and that will give you the ketone. as an intermediate. So you already have the R of the Grignard being added. So you could see it there. Now it's going to react with the second equivalent of this, the second equivalent of the Grignard to attack the same way. It's going to attack the carbonyl carbon, breaks up the pi bond, gives you the alkoxide. Obviously, there's no leaving group here. So that's why the O- will get stuck to not be able to restore the carbonyl bond, because the carbon cannot have 5 bonds, obviously. So the alkoxide automatically will be protonated with a second step, H3O plus, to give you the tertiary alcohol. You always get a tertiary alcohol when you react a Grignard or alkyl lithium with acid chloride or ester. What's another way of getting a tertiary alcohol using Grignard? Reacting a ketone with Grignard or alkyl lithium will get me access to a tertiary alcohol. Another method, Grignard, that gives me access to alcohol is to use ethylene oxide or epoxide. We've seen this functionality when we have an alkene reacting with peroxyacetic acid or peroxy benzoic acid, or the MCPPA, metachloroperoxybenzoic acid. Once we make that epoxy group, the Grignard will pick the carbon that is less sterically hindered. Now, of course, this example has equivalent carbons, so it doesn't matter which carbon to pick. But if I have epoxy group and I see one of the 2 carbons that's attached to the oxygen is more substituted than the other, avoid that carbon. It will be sterically hindered for the Grignard to attack. It's bulky reagent, so it will pick the less sterically hindered, the less crowded one. And once it attacks it, it breaks up the C single bond O. It makes an alkoxide. Upon protonation, you get the primary alcohol. You always get a primary alcohol when you have the ethylene oxide. Obviously, I may have a substituted carbon that will obviously change the outcome of that alcohol structure. Keep in mind, Grignard will always attack the less sterically hindered carbon of the epoxide. That's always the case. And here's an example where you see it's a butyl magnesium bromide attacking the one of the 2 carbons, which it doesn't matter here which one you pick. It breaks up the C single bond O, and that makes an alkoxide. Upon protonation, you get the alcohol. Do not put the Grignard and the H3O plus in the same step, because you basically reach a dead end when you do so. The Grignard will just pick up the H from the H3O plus, and it will give you RH, which is the alkane. You don't want to do that. H3O plus has to be written as a step number 2 after you are done with the Grignard or the alkyl lithium reaction. This is another organometallic reagent that's called lithium dialkyl cuprate. There's another name for it, which is the Gilman's reagent. Now, you're not going to have an application for this reagent in this chapter, but you will see it later on in future chapters. The purpose of it is to couple with the R of that R2 copper lithium with an R of an alkyl X to give you a C single bond C. The beauty of this reaction that the coupling of those 2 R group could be actually not easily done using other reagents. So the Gilman reagent will be an easy way to do so. How do you make it? 2R lithium plus copper iodide. The outcome of that will be lithium iodide as an ionic bond structure, and R2 copper lithium. There is a drawback for this reagent. That is, you waste one of the R groups of the R2 copper lithium, and you only utilize one of them. So you utilize one to couple, and the other one will go to waste. Obviously, the purpose of using such reagent is to control the chemistry, as it is it's not as reactive as the alkyl lithium, because this reagent is controlled in a way that the copper slows down the reactivity of the carbon that's attached to it. So, and as I mentioned, this reaction will not be used in this. This reagent will not be used in this chapter. Rather, we will see it in future chapters. Here are the list of limitations of any of those organometallic reagents. So whether you're talking about acetylides, or talking about Grignard, or talking about alkyl lithium, the most important limitation that we need to highlight is not to use product solvents. Why? Because if I have an alcohol, or I have water, or I have a group part of either of the two reactants, the Grignard or the carbonyl structure that has an acidic hydrogen, that acidic hydrogen will be picked up by the Grignard, and you quench the Grignard to make an RH, and that's it, you're done. So if you have an alcohol group, or an amino group, or a thiol group, or an acetylide, or an alkyne H, all of these are acidic hydrogen. You don't want to have those in the presence of a Grignard moiety available to attack a carbonyl structure. The other thing is the Grignard itself reagent, you cannot have a carbonyl or a cyano or a sulfoxy or an N double bond O. Any of these can actually interfere with the electrophilicity of the carbonyl structure. So it's very important that when you have a Grignard as reactant number 1 attacking a carbonyl group of a reactant number 2, the Grignard reactant, you cannot have a carbonyl, you cannot have a cyano, you cannot have an S double bond O, you cannot have an N double bond O. Why? Because that will confuse the reagent from attacking the second reactant carbonyl versus the attack on its own structure. So you're going to end up having the Grignard reacting with itself, and that will obviously give you an undesired product at the end. So these are the limitations. And remember, we said all of these reagents are very sensitive to water and very sensitive to oxygen. So when we do these reactions, we have to have overnight dried glassware. We want to make sure that the reaction is being protected without having it exposed to air. We want to make sure that the glassware are not wet. There's a purpose for all that, because these reagents are very strong bases and strong nucleophiles. The presence of an acidic hydrogen will just quench the reagents and will convert them to RH, which is going to be the end of that reaction and will not get you to the point where the Grignard or the alkyl lithium attacking a carbonyl of an aldehyde or a ketone or an acid chloride or an ester. And you could see here clearly the presence of water, even in the air, will actually quench the Grignard. So you have the RNGX attacking the water. The point of attack is going to start with the negatively charged carbon, obviously, attacking the hydrogen. That will give you RH and the hydroxide. So you end up having the same thing when you do alkyl lithium in presence of water. So you could see here how it is a very, very strong limitation that we need to keep in mind when we have any of these organometallic reagents. You could see here also butyl lithium reacting with an alkyne H. That's going to actually drive the reaction to the right due to the fact that you are making an alkane that has a pKa of about 50. So compared to 25, obviously the acid-base equilibrium will favor the alkane structure. So again, we're basically killing the Grignard or the alkyl lithium if we have an acidic hydrogen around that moiety of the Grignard or the alkyl lithium. All right. So in addition to the option of organometallic reagents attacking a carbonyl of an aldehyde or a ketone or an ester or an acid chloride, we also have another option how we can get an alcohol using a carbonyl structure to be reduced. So reduction of a carbonyl, depending on what carbonyl we're talking about, and that's what we see here, it's going to give me an alkoxide, and that alkoxide upon protonation will get me the alcohol. So you can see here that there are two options. If I have an aldehyde or a ketone, the aldehyde will always give me access to a primary alcohol once it's reduced. The ketone, once it's reduced, gives me access to a secondary alcohol. So the reagents that we use to reduce carbonyl structures usually are hydride reagents. So they do have an H minus due to the presence of the metal, sodium and lithium. It's going to make the H more of a nucleophile than it is actually a basic hydride. So if you would use sodium hydride or lithium hydride, these are usually used to deprotonate an acidic hydrogen. But when you use a sodium borohydride or lithium aluminum hydride, lithium and sodium, they love the chelation to the carbonyl oxygen. and that actually forces the H minus to attack the carbonyl carbon rather than looking for an acidic hydrogen. So that's usually the case when you see a sodium borohydride, lithium aluminum hydride. That means they're going to attack a carbonyl carbon to add an H minus to it. So let's see examples. So if I have the sodium borohydride, usually it's used for the case of an aldehyde or a ketone. I cannot use it for carboxylic acid or an ester due to the fact that the sodium borohydride, it's milder reagent compared to the lithium aluminum hydride. Sodium borohydride, NaBH4, can only reduce an aldehyde to a primary alcohol and ketone to a secondary alcohol. It cannot reduce an acid, and it cannot reduce an ester. We will see what will the option be if I want to reduce those two functionality to the corresponding alcohol. Now, here's the short version of the mechanism. So you can see the H minus basically attacking the carbonyl carbon, and that gives you the alkyl side. Upon protonation, you get the alcohol. That's usually the mechanism when you have a hydride addition to a carbonyl structure. Of course, the purpose of why it's H minus added to the carbonyl carbon is due to the chelation of the oxygen to the sodium or to the lithium. And that's why the H minus will not have the chance to look for an acidic hydrogen. It will be just added to the carbonyl carbon in a nucleophilic addition pathway. So here's a list of examples. You can see that aldehyde can be taken to a primary alcohol. Sodium borohydride can be used in alcohol solvent or water. So usually it's an alcohol due to the fact that the organic compound will be more soluble, obviously, in alcohol solvent. So don't think of the alcohol solvent as it's a source of hydrogen. No, the hydrogen will come actually from the sodium borohydride as an H minus being added to the carbonyl. So it's important that we keep this in mind, that the sodium borohydride is the source of the hydride, and the ketone will be reduced, and you get a secondary alcohol out of it. You could do the same exact chemistry if you replace the sodium borohydride with lithium aluminum hydride, much stronger reducing agent. There is no reason to use the lithium aluminum hydride if we have sodium borohydride that I want to reduce an aldehyde or a ketone. But when will I use lithium aluminum hydride? I use it if I want to reduce a carboxylic acid or if I want to reduce an ester. And these two functionalities will be reduced to a primary alcohol. How come? Sodium borohydride is too weak. It's less reactive compared to the lithium aluminum hydride, which is much more powerful. Whether you say Li lithium aluminum H4 or you say LAH, it means the same thing. So LAH is actually acceptable abbreviation for the lithium aluminum hydride. So you can see here an example of an ester. So you end up making the OH out of the carbonyl, and this OCH3 leaves as an alcohol product. So you end up making a primary alcohol every single time you reduce an ester or a carboxylic acid. And here you can see the difference between the two reagents. So lithium aluminum hydride can reduce aldehyde, ketone, ester, or acid. That's how powerful it is. And of course, the ease of reduction will be easier to reduce an aldehyde than a ketone, than an ester, than a carboxylic acid. So that's important to keep in mind. While sodium borohydride can only reduce an aldehyde or a ketone. The aldehyde will be reduced to the primary alcohol, the ketone will be reduced to the secondary alcohol. If I reduce an ester or an acid in presence of lithium aluminum hydride, they will be taken to the primary alcohol. And here's a comparison. You can see that the sodium borohydride, if it reacts with a keto ester, it will not touch the ester group. It will leave it it will basically not reduce it at all. It will reduce the carbonyl of a ketone instead to the secondary alcohol. What if I have a lithium aluminum hydride in the presence of the same reactant, which is the keto ester? It will reduce both the ketone to the secondary alcohol and the ester to the primary alcohol. Keep in mind that the alkoxy group will leave as alcohol, and whatever left behind will be the C double bond O becoming a CH2OH. The last method that I can also use to get an alcohol is the reduction using hydrogenation. So catalytic hydrogenation H2 in presence of nickel or platinum or palladium. They've been used to reduce an alkene. I could also use the same method to reduce a carbonyl of an aldehyde or a ketone. And I'm going to mention this one more time. You cannot reduce an ester or an acid using this method. You could only use this method when you want to reduce an aldehyde or a ketone. So you can see here clearly that if I have an alkene and a carbonyl of an aldehyde, I will not have a reduced selectivity in terms of reduction. I will reduce the alkene to the alkane, and I will reduce the aldehyde to the alcohol. What if I want to reduce the aldehyde without touching the alkene? Then I can use sodium borohydride. Sodium borohydride, it's known not to reduce an alkene. It can only reduce an aldehyde or a ketone, and that's important to keep in mind. Lithium aluminum hydride can also do the same job, but since the sodium borohydride can do the job, why you want to use a much more powerful reagent that we actually may have difficulty running the reaction due to the explosivity of the reagent itself, the lithium aluminum hydride. It's much easier to deal with sodium borohydride than lithium aluminum hydride. So these are the methods of prep. So we've seen the organometallic reagents pathway to give us alcohol. We've seen the sodium borohydride reduction of an aldehyde or a ketone. We've seen the lithium aluminum hydride that can reduce an aldehyde, ketone, ester, or an acid. And we've also seen the hydrogenation, the catalytic hydrogenation method. It can reduce both the alkene and the aldehyde or ketone functionality to the corresponding alkene in the presence of alkene and alcohol in the presence of a carbonyl of an aldehyde or a ketone. Another group that is similar to the alcohol is the mercapto group. What's a mercapto group? Is when you have an SH group. So instead of OH that gives me an alcohol, a hydroxy, I have an SH that's a mercapto group. The functional group of mercapto makes compounds that are called thiols. So those thiols, the way how we name them, we basically have to find the longest chain of carbons, and the first carbon has to be the carbon that's attached to the sulfur, obviously. So in the case of CH3SH, that will be called methane thiol, or the common name would be methyl mercaptan. Methyl mercaptan. If I have a 4-carbon chain, that will be butane 1-thiol. If I have the common name would be butyl mercaptan. And if I have a thiol and an alcohol, alcohol becomes the priority in numbering the structure. So therefore, the SH becomes a mercapto group as a substituent. So the thiol will be when you have a parent name, mercapto when you have the SH as a substituent. So that the name would become 2-mercapto ethanol, 2-mercapto ethanol. The important thing that I want to make sure that we keep in mind is the acidity of SH versus OH. OH has a pK of about 16. So when you deprotonate that, it's going to give you an alkoxide. The alkoxide will be less favored in this reaction due to the fact that the pKa value of the alcohol is going to be higher than the corresponding water. But if I use the same base and deprotonate a thiol, look what's happening. The pKa of the thiol usually is about 10. And when I produce the conjugate base, I'm going to end up making a water as a conjugate acid. The pKa difference will force the equilibrium to go to the thiolate structure. So that's important to keep in mind, that the thiol group is much more acidic. It produces much weaker base compared to the alkoxide. So S minus, when we see it, we treat it as a strong nucleophile, not a strong base. That's the difference between alkoxide and thiolate. Thiolate are not good bases, rather they are strong nucleophiles. Here's another example, benzene thiol, reacting with OH minus, pKa drops down to 7.8 due to the stabilization of the conjugate base. So when we draw the benzene thiolate, this structure has several resonance forms, and that's what makes the pKa of the conjugate acid a stronger acid. The pKa will be actually less compared to an alkyl thiol. And of course, the equilibrium will favor the benzene thiolate due to the fact that the benzene thiol has a pKa of 7.8, while the water has a pKa of 15.7. Acid-base equilibrium usually favors the higher pKa side, weaker acid. That's usually the case. When we use them as nucleophiles, obviously they attack an alkyl halide, preferably to be a primary or a methyl X, and that will go through an SN2 pathway. So the reaction is very straightforward. Usually we have an alkyl S minus or a sodium hydrosulfide that can also be used as a nucleophile to make a thiol or to make a sulfide. When we say sulfide, that means I have an RSR. That will be similar to what we say for an ROR, which is an ether. The biological application of those thiol groups, it's important to keep in mind that when you link two thiol groups together, you make a disulfide, and that will be called an oxidation. When you do the opposite, breaking up a disulfide bond, that will produce two thiol groups. That will be a process of reduction. We don't do this really in lab when it comes to organic chemistry set of experiments, but we see this as a biological example of where these groups are being utilized. And of course, the disulfide bonds could actually contribute to intermolecular forces of some of the proteins where we see their properties being actually influenced with in the presence of such group. And that's the story of chapter 10.